Hi everyone, I'm Federico and welcome to the presentation of this joint work with Nicolò, Tommaso, Roberto and Stefano. Motivated by the recent shift from second to first price auctions in the online advertising market, we study repeated first price auctions in an online learning framework. In particular, we will take the perspective of the bidder, that we will call the learner. Okay, now let's introduce the model. At each discrete time step t, a new auction takes place, meaning that an adversary, let's say in nature, privately generates two numbers, Vt, that is the value of the item on sale for the learner, for the bidder, and Mt, that is the bid of the competition. Then what the bidder does is to post a certain number Bt, and finally, a first price auction takes place, where the utility of the bidder is written here, and it's non-zero if and only if it wins the auction. So Bt is greater or equal than Mt. And the net utility in this case is given by Vt, that is the value of the item, minus the price paid, that is Bt, the bid. This is because this is a first price auction. And then at the end of each auction, the bidder receives some feedback. Now let's see here an example. The competition bid 50 cents, the bidder bid 75 cents. So it wins the auction and it gets a net utility of 25 cents. Now there are two features that are important and that we want to stress. So first, this bid is done without actually knowing what is the value of the competition, Mt, clearly, but also without knowing Pt. The reason is that in many cases, the learner only has an imprecise knowledge of the value of the item it is bidding for. So this is something that is only revealed at the end if the auction is won. The second feature I want to highlight is that the feedback that the bidder receives can be regulated by the platform. So let's say the transparency policy of the platform will have an influence on the feedback, and this is something we want to understand. Okay. From the bidder perspective, clearly the natural goal is to maximize the total utility across all time steps bid. Since we are using an online learning perspective, it's more natural to focus on a different and in some way and actually equivalent objective, that is minimizing the regret. So here we can see that the regret is defined as the difference between the utility of the algorithm in orange and the utility of the best fixed bid in hindsight. So we are giving to the benchmark the benefit of hindsight, but we are constraining it to use always the same bid, as it is standard in online learning. Now, let me comment a bit this formula. At each time step, the utility is between -1 and 1, meaning that the total utility and then also the regret is order of t. Now, for the learning to happen, let's say, we require that the regret RT grow sublinearly in the time horizon t, meaning that the average utility converges to that of the benchmark. Now, note, a good algorithm wants to enforce sublinear regret with respect to any possible input sequence. What we do in this paper is to fully characterize the minimax regret rate for various feedback and data generation models. Okay, now let's see what are the feedback models that are natural in this repeated first price auction setting. So we have two, let's say, numbers, two quantities that the learner is interested in receiving as feedback. Mt, the competition, and Vt, that is the value of the item. Now we introduce, let's say, a benchmark feedback model. This is the full feedback model, where at the end of each auction, both MT and VT are always revealed. But this is definitely not natural. So let's start looking into more natural feedback models, starting from VT. Okay, the value of the item for sale is kind of natural to assume that it can only be measured by the learner if the auction is won. So we observe VT only if the auction is won. For what concerns MT, now the amount of information that is disclosed at the end of each auction about MT depends on what the platform decides to disclose about the bids it received. So for example, if the platform decides to always reveal all the bids, then from the learner perspective, we are in the transparent feedback row. MT is always observed at the end of each auction. On the other extreme of the spectrum, in the bandit feedback model, we have a platform that decides to not disclose any information about the bids received, so that MT is never observed by the learner. As an intermediate and meaningful feedback model, we have the semi-transparent feedback model. That is something that is actually implemented in practice, where the platform always reveals the winning bid. So from the bidder perspective, this means that MT is only revealed if the current auction is lost. So these are the 4 feedback models we are going to study in this paper. Okay, we have specified which are the feedback models we study. Now let's see at the environment, the data generation models. There are, like from the literature, we have 2 paradigmatic models. The stochastic model, where VT and MT are drawn IID from a fixed but unknown distribution, and not that VT and MT can be arbitrarily correlated, or the, let's say, other more demanding adversarial model, where VT and MT are generated by an oblivious adversary in an arbitrary way. Now, for the sake of completeness, and also because we will see this will bring a meaningful result, we also study the smooth versions of these 2 models. Where what do we mean by smooth? So here is the definition, is a property of random variable and measures. We are going to require that that the environment cannot generate pairs that are too concentrated. So this is a way to avoid point masses. Okay, before presenting our results, let's just think about the technical challenges of this problem. Now, in the classical online learning model, what happens is that we have a finite action space, so a number of arms, also called bandits in some applications, and the learner has only this very narrow action space to choose from that is typically finite. But in our problem, this is not the case, because the bid space is the 0-1 interval. A possible fix to this infinite action space is provided in the literature by handling regular objectives. So for example, Lipschitz or strongly convex functions. But as we will see in the next slide, this is not the case in our problem. The second challenge is posed by the feedback structure. Now, transparency regulates the ability of the learner to reconstruct counterfactual information. And counterfactual information are useful because with access to it, then we can use the machinery for the prediction with expert framework, also called full feedback learning, where the regret rate scale only logarithmically with the number of actions. If we do not have access to counterfactual information, then we are in the bandits realm, where the typical regret rate is order of square root t times k, where k is the action space. But note once again that these results are for finite action space, while in general, as we already mentioned, this is not the case for us. Okay. Now, this figure kind of gives an intuition of which are the difficulties in trying to, let's say, discretize our action space. Okay, on the left, we see two different profiles of the utility function. In the top plot, we see that if Vt is larger than Mt, then we have this discontinuous behavior, and the jump, let's say, is from a lower value to a higher value. On the contrary, if Mt is larger than Vt, meaning that to win the item, the bidder has to pay way more than the value of the item, thus incurring in a negative utility, then let's say the jump is on the other direction. This is important because if we sum up these two utility profiles, we see that the actual objective, that is the sum of the utilities, can have the specific shape that is represented on the right, where we have a narrow region that could be arbitrarily small, where bids provide a good approximation of the best bid B star, and all the other, like the rest of the interval, does not provide good approximation of the optimal bid. So we see that the fact that the utility function is not continuous, is not Lipschitz, and it's actually not even one-sided Lipschitz, makes quite hard to find a way to discretize the action space in such a way that it's possible to use the techniques, the online learning techniques that are able to handle a finite support of the action space. What we do in this paper, from the technical point of view, very briefly, in the IID case, we exploit the structure of the utility function to build a sample-based non-uniform grid of candidate bids. So we exploit the structure of the utility in such a way that it's possible in initial phase to observe some sample, and starting from this sample to find a good set of candidate bids, where this jump behavior depicted in the right plot is not present. In the adversarial setting, where we do not have stationarity, so the Vt and Mt are not correlated across time, actually, we exploit smoothness, so the regularity assumption we mentioned earlier, to guarantee that the expected utility is Lipschitz. So we are no longer looking at the actual sum of the utility, but we are looking at the expected utility. And with this assumption, then everything is Lipschitz, and it is possible to use a uniform grid. Okay, so this is just a glimpse on the techniques used in our algorithms. Now let's look at this table that presents our results. Okay, how do we read this table? On the rows, we have depicted the various feedback models that we described, while on the column, we have the environment, the data generation model. And what we have is a full characterization of the minimax regret rates that are achievable for each one of these feedback environment combination. And with the characterization of minimax regret rate, I mean that all our algorithms have upper bounds that are matched by some hard instance, some lower bounds. Okay, what we realize is what we see from this picture is that there are, let's say, three types of problems that arise from this variant combination. So in particular, we have the, let's say, green entries, the easy problems where it is possible to achieve a regret that scales as square root t. Then there are the hard problems, that are the orange one, where I have a worse but still sublinear regret rate. And then there are the impossible problems, that are the red ones, where no learning is possible. Okay. Another interesting feature is given by the nature, by the, let's say, the exponents of the regret rates. Because square root t, t to the 2/3, and t are the same rates that we recover in other famous online learning problems, namely online learning with feedback graph and partial monitoring. Differently, there are other economic problems that have richer behavior. So for example, there are smooth auctions and bilateral trade, where it is possible to have, for instance, minimax regret rate that have a rate of t to the 3/4. So there is an interesting separation between this problem and other similar economically motivated problems. Okay. Now, in this slide, we want to extract some qualitative information about the impact of transparency policies on the learnability of the problem. So we see that the first two rows are kind of indistinguishable, meaning that if the platform decides to disclose all bids, then this is equivalent to, from the, let's say, minimax regret rate, this is equivalent to allow the learning to receive full feedback, which is something extremely strong, because in full feedback, VT is always revealed. On the other hand, if the platform decides to only disclose either the winning bid or no bid at all, we see that there is like a deterioration of the regret rate. And another interesting feature is that while smoothness is crucial to ensure learnability in the adversarial setting, it has a very mild influence in the stochastic setting, as it only improves the rate in the bandit feedback. Okay, so I hope you enjoyed the talk. Thank you for your attention, and I hope to see you all in Vancouver.